Hello everyone, I'm Tanut. Today I will discuss about my research on Gittins theorem under uncertainty aversion. And this is a joint work with my supervisor, Sam Cohen. Before starting our discussion about mathematics, I would like you to consider the following example. Suppose we have two coins with unknown bias, and we need to choose between those two coins to gain £1 for tossing a head. Suppose we have the following observation. The first coin was tossed for 3 times with 2 heads, and the second coin was tossed for 3,000 times with 2,000 heads. Which coin would you choose? I guess most of you would have your first instinct to choose the second coin. And the reason for that is humans often have a bias toward a less certain choice. We often prefer the choice that we know better. So I would like you to consider and keep this example in your mind, and we will come back to this example in a minute. But now let's ask a slightly different question. What shall we do if we need to repeat this game for 1,000,000 times? This problem, when you need to repeat the game, is basically the concept of a multi-arm bandit problem. So the idea of multi-arm bandit problem is that you go to the casino, you have an M machine, and you need to play one machine at a time. When you play the machine generates a cost from a fixed distribution. However, you don't know the distribution. You only learn about the distribution as you go along. To solve this problem, Gittins basically proposed the idea of Gittins index theorem. Okay, originally, if we try to solve this problem, we need to solve the backward induction, which involve m-dimensional problem due to you have m number of slot machine. Okay, but Gittins basically say that you could just compute the index on machines separately, and when you can establish the index of the machine, then you could just choose to play the machine with the lowest index. Now, what the index really look like? What does the index really mean? So you may view the index as consider the distribution as composing by 2 parts. The first part is the posterior mean, and the second part is the posterior variance as the underlying state for the Markov decision process. So the index can be approximated by your posterior mean, and then you take the reward from the posterior variance. Okay, and if you think what posterior variance really means, in some sense, is basically uncertainty about our estimate. And therefore, in the multi-arm bandit problem, we often see the uncertainty as an optimistic thing. We usually see the uncertainty as a good thing. But previously, in our first discussion about coin tossing, we basically see the uncertainty as a bad thing. This seems to give a contrast between the two approaches of tackle the problem. Also, other algorithms like UCB also view the problem in the same way that they look at an uncertainty as a good thing. So our objective for this talk is try to understand how could we incorporate the concept of uncertainty aversion and the optimistic toward uncertainty for learning. Okay, so we will try to establish the Gittins index theorem under an uncertainty aversion setting. Okay, so how could we do that? We just think about the classical thing we often do in math finance, that is we consider the worst case measure. And this corresponds to consider a nonlinear expectation. But this problem is a dynamical problem. And in order to solve a dynamical problem, we often require a tower property, okay, via to use the dynamic programming principle. This means that we need to consider a consistent nonlinear expectation which have the tower property satisfied. And if one go to the literature, the problem about nonlinear expectation is that you need to identify the filtration in advance. However, in the multi-arm bandit problem, when you play the bandit, you will observe the information as you play. So you cannot control the filtration that you observe the information. Okay, so you control the filtration that you observe the information, and so we need a slightly different way to view this problem. In order to do that, we basically ask ourselves, what is the crucial key for Gittins index theorem? And the crucial key is independent. Okay, so now we think, what can we describe the filtration in the independent problem? We can consider the filtration for each arm about the information that you obtain from each arm. And then you consider a product measure as a space that you consider. Then you obtain a nonlinear expectation operator in that way that you can preserve the independent structure. However, even though we start from a consistent nonlinear expectation, so we start from a consistent nonlinear expectation with a filtration that we have to define for each machine, and we define the joint space, this operator does not satisfy time consistency, which means that we can apply the dynamic programming principle and we can approve anything. So the idea is we ask ourselves again, what does it mean for thing to be the best? That is the idea of how we solve the dynamic programming principle. So we basically get a simple answer, is that every time when you try to find that thing is the best, we try to find the lowest price, which is the real or deterministic compensator. Okay, but we ask ourselves, well, nothing special about real number. So we basically propose the idea to consider a random compensator, and if we can prove that your random compensator is minimum, we say that this is a C optimum for the decision making. And we can require even more to have the compensator to be a process and have a predictability, but we probably don't go to that in this talk. By considering the compensator, it surprisingly preserves the time consistency even though the operator failed to satisfy time consistency. Okay, and when we can get that structure of the optimal, we can establish the Gittins index theorem under the robust version. So we can say that there exists the index such that playing the machine with the minimum index gives you a C optimal answer. Okay, and this index can be evaluated by solving a nonlinear optimal stopping problem, or you could see that as the optimal stopping problem, taking the infimum over stopping time, and you have a family of measures that you consider. Okay, so now let's try to see what Gittins index really mean. Okay, how you interpret the idea of the index. So to interpret the idea of the index, we consider a coin tossing example. We have a Bernoulli Bandit with the unknown parameter. And at each step, we basically consider the measure using the credible set or confident interval of size k as our estimate. And we can then define a nonlinear expectation by using the backward testing. After that, we can show that the index can be written as a function of the estimated probability and the number of observations, and we write it in terms of 1 over square root n, just for the notational simplicity. Now we ask ourselves, what does it mean for the index to evaluate uncertainty? So we will give a plot between gamma and p to see how we evaluate uncertainty. And the plot shows that when beta, which is the discount factor, is 0.99 and k equal to 0.8, where we consider the 80% confident interval, we basically could see the plot of the difference between gamma and p in the following. You can see that when 1 over root n getting close to 0, when you become certain about our estimate, the curve becomes flat. So index is basically the estimated probability. However, when you have like the large number of observation, small number of observation, you could see the mixture of both behavior. You could be either optimistic or you could be pessimistic. The blue thing means that you are optimistic toward uncertainty because gamma minus p is negative. Now you basically consider uncertainty as a reward. But when gamma minus p is positive, you see the red surface. That means that you penalize the uncertainty. Okay, so you say that when the game is good, you prefer to be optimistic, and when the game is bad, you become pessimistic toward uncertainty. Okay, so in terms of simulation, does the Gittins really help? Or adding the robustness really help in terms of decision making? And the answer is yes. We consider about 50 bandits over 10 to the power 4 trial, and we compare with the existing method that also used in the multi-arm bandit problem from statistical science. We basically could see that adding an uncertainty aversion, you could reduce the expected regret through time, but when you add the aversion too much, you basically often terminate in a wrong choice, and you basically suffer from more regret. So this is the end of my talk. Thank you very much for your attention. So basically what we propose is we basically propose an idea to understand the optimality when we have an inconsistent operator and we consider the decision making under a multiple filtration. We also derive the index problem, which involves a low dimensional problem, which you can solve computationally. And also our model can take into account of the desire to learn and uncertainty aversion, which could illustrate the agent preference when you try to make decisions toward learning. Thank you very much for your attention.